Well, Charlie, thank you very much for that kind and greatly exaggerated introduction. And ladies and gentlemen, it's a pleasure to be here in foggy and chilly Canberra after Phoenix, Arizona. So whether or not we're alone in the universe is surely one of the oldest questions that human beings have ever asked. But for the majority of history, it's belonged to the provinces of religion and philosophy. But 52 years ago, last April, 52 years ago, it became part of science when a little-known astronomer, radio astronomer, by the name of Frank Drake, began to sweep the skies with a radio telescope in the hope of stumbling across a message from an alien civilization. And this is a picture of the said Frank Drake in April 1960 with the Green Bank radio telescope in the background, which is what he used. This rather quixotic quest wasn't done on a whim. Radio telescopes were a byproduct of World War II, in particular radar research. And in the immediate post-war years, the astronomers and radio engineers began building these big dishes. And they soon realized that within a few years that they had in their grasp instruments capable not just of communicating across terrestrial distances, but across interstellar distances. And then in 1959, in a landmark paper in the journal Nature, Giuseppe Ciccone and Philip Morrison at MIT suggested that astronomers could use radio telescopes to search for radio messages coming from alien civilizations out there in the galaxy. And they conceded that although the probability of success of this search would be exceedingly low, nevertheless, if nobody tried, the probability would be zero. And so Frank Drake took up the challenge, knowing that with an instrument like this, he did have the power to detect radio messages should an alien civilization be beaming them at us with an instrument presumably rather more powerful than this one. And so thus began the subject of SETI, the search for extraterrestrial intelligence. And I'll be using this acronym SETI many times in the lecture today. And so it addresses the question about, is there anybody out there? And if there is, are they trying to communicate with us via radio? Now, most people have heard about SETI, and I expect you have come here today for the simple reason that you've heard about it too. A lot of people get their information about SETI from Jodie Foster. Here she is, starring in the movie Contact. So this movie was based on the novel written by Carl Sagan. He was like an arch-evangelist of SETI. And she plays the part of the starstruck astronomer who manages to pick up the message from ET. And by and large, this movie follows scientific respectability. It's more or less what the SETI community do, with one obvious exception, that the great moment of discovery when Jodie finally hears the message from the aliens is picked up on headphones, which is why she's doing this. She's wearing headphones to discern the messages coming in from space. Well, when Frank Drake started this in 1960, he had a couple of loudspeakers in the observatory, and then if he picked up a signal, they would start shuddering and booming. Today, SETI astronomers routinely monitor about 1 billion radio channels simultaneously. And so trying to pick this up in headphones is pretty ludicrous. It's like listening to a billion radio stations all at once and picking out the one that's got the message. So, but that aside, the movie is more or less in the direction of what the SETI research program has been doing. Now, a number of radio telescopes have been used for this purpose. The one closest to here is Parkes in New South Wales. This movie was, dish was famous for the movie called The Dish. I'm sure you've seen that, which is about the first moonwalk. But it's also been used on and off for SETI searches. And let me just tell you what they do. A typical SETI search would consist of manipulating a radio telescope like this. You'd have a wish list of stars, an inventory of likely-looking sun-like stars in our neighborhood of the galaxy. Point the telescope at a particular star, listen for about half an hour. You don't hear anything, move on to the next one, and so on. That's what they do. In the event that they pick up a signal, then the procedure is to tip the dish a little bit to one side and then back again. And if the signal fades and comes back on, then that is good news. And then to follow it for a while to see if it is following the rotation of the Earth relative to the stars rather than relative to the sun, which would indicate it's coming from deep space. And then using another radio telescope on a different part of the world to cross-check. And so that's a procedure. It's really rather time-consuming, which is significant for reasons I'll explain in a moment. This is another dish that's often used by, for SETI purposes by radio astronomers. This is the Arecibo radio telescope in Puerto Rico. It's the biggest in the world. It's not steerable, though. It's a dish that's just stuck staring straight up at the sky. So as the Earth turns, it monitors a strip of sky. This was also famous for featured in the movie with Jodie Foster and also in the James Bond movie, GoldenEye. So all of this is very familiar from Hollywood. The jewel in the crown of the SETI program is this array of radio telescopes here in Northern California, a place called Hut Creek. And this is called the Allen Telescope Array because Paul Allen, co-founder of Microsoft, gave $35 million for this to be built. The plan is eventually there should be 350 of these dishes, and if it reaches its design specifications, it will be better than any other radio telescope on the planet for this particular job. 42 have been completed now, and it's operated by the SETI Institute in California, and they've run out of money. So if you've got any rich friends who are interested in cornering the market on searching for ET, just get in touch with me or send me your check. I'll pass it on to the people who need it. So this array here is currently hibernated or mothballed whilst they're waiting for the $2 million per year running costs. So it's, in my view, a tragedy that this wonderful system, this instrument here, is lying idle when it could be used for SETI purposes. Anyway, the upshot, that's just a broad brush summary of what SETI has been up to in the last 52 years. And of course, you'd know all about it if they have been successful. That is to say, after 52 years, all the radio astronomers have got to show for it is an eerie silence. Hence the title of my book, which I wrote for the 50th anniversary of SETI, because I wanted to do a number of things. One was to give a critical evaluation of the SETI program and a little pat on the back to my friends who do this stuff. But then I wanted to ask, whilst we're waiting for this heroic and tiny band of radio astronomers to come up trumps and open the bottle of champagne that they keep on ice, whilst we're waiting for that, is there anything else that the broader scientific community can do to expand the search for ET? Must we leave it just to this little group? And the answer is yes, there's a lot of things we can do. I'm going to tell you about it in a moment. So the fact that there is an eerie silence, what does that mean? Does it mean that we are, in fact, alone in the universe, or at least alone in the galaxy after all? Or might we be looking for the wrong thing or in the wrong place at the wrong time? Now, I think there's a very good reason why SETI, Radio SETI, as it is described to you, would not have succeeded. It's a very simple reason, and that is ET may be out there, but ET doesn't know that we are here. Now, what's the reason for that? Well, let me take you through some simple arithmetic. I regard Frank Drake as one of the most optimistic scientists in the world. Who else do you know has designed an experiment, run it for 50 years, got a null result, and is still upbeat about the future? And he is. He's now in his 80s. He's still an active SETI radio astronomer. I saw him just a couple of weeks ago sitting at his desk. He's still in the game, and he remains confident that this method of searching for ET is going to succeed. And so if you ask a SETI optimist like Frank, well, give me a guesstimate of how many civilizations are out there in the galaxy transmitting radio messages, of course, nobody knows. He has no basis for giving me any number, as we'll see in a moment. But if we take his number, which is 10,000 in the Milky Way at this time, then a bit of simple mathematics can tell you how far away the nearest such civilization is likely to be. And it's a few hundred light years away. So let's take 1,000 light years as a round figure. So maybe over there, somewhere in the galaxy, 1,000 light years over there, is a community of aliens interested in communicating with us. You can imagine that they're going to be far in advance of us. They've got some super-duper instruments, and they can observe Earth very closely. And they know there's intelligent life on Earth. How do they know it? Because they can see the pyramids and the Great Wall of China and the beginnings of agriculture. But now we hit a problem, that the fastest speed in the universe is the speed of light. You can't observe another planet in a time less than it takes for the light from that planet to reach it. So if they're looking at Earth now, they see Earth as it was 1,000 years ago. There were no radio telescopes 1,000 years ago. So put yourself in the position 1,000 years ago of a SETI enthusiast in this hypothetical planet going to the government or the funding agency and saying, we know there's intelligent life on that planet over there, and we think that any millennium soon they will have radio technology. Can we have some money to start transmitting messages? And I can tell you what the answer would be. I know the committee would deliberate on this, and they say, that's a very wonderful project. You come back in 1,000 years or 10,000 years or whenever you know that they have the capability of detecting our messages, and we'll give you the money. So when will ET, over there, 1,000 light years away, know that we are here with our radio telescopes? And the answer is when our first radio messages reach them. Now, every time you broadcast a radio or a TV show, some of the radio waves leak out into space. We can't do anything about that. We can't get them back. They go off out into the galaxy, and in 100 years, they've traveled 100 light years and so on. So we imagine that there is this sort of wavefront of the first feeble radio messages broadcast on Earth that have leaked out into space, and they've got about 100 light years out there. So quite a long way to go still before they reach this hypothetical nearest civilization. In about another 900 years, maybe ET over there will start broadcasting to us, and then in another 1,000 years, we pick up their first message. So you see the problem. The fact that it's silent out there might simply mean that it's not worthwhile any extraterrestrial community speculatively beaming messages at a planet on which they know there's intelligent life, but they don't know that there's radio technology. So that's the problem. So how do we get around this? Is there something we can do? And I think the answer is yes. So now let me take you through this formula here. This is Frank Drake, as he appears these days, as standing in front of his eponymous equation. This is the equation he uses to deduce his 10,000, and this is how he comes up with that number. Now, this is not an equation in like the physics sense of the term. This is more a list of things we don't really know. So it's a catalogue of our ignorance. And when I got interested in SETI way back in the 1960s when I was a student, we really didn't know any of these numbers. Well, we're now in better shape. The first one is the rate of star formation in the Milky Way. We know that number rather precisely now. It's about 7 per year. The next one is the fraction of those stars with planets. Again, in the 60s, nobody knew whether there were any planets outside of the solar system. There was a theory that the formation of planets was some freak event that would not be likely to occur anywhere else in the galaxy. There was an alternative idea, which is that most stars have planets. And I think probably astronomers believed the planets were out there, but they didn't know. Well, as you're probably aware, in the last 20 years, we've actually found many of these extrasolar planets. So that's the fraction of stars that have planets, and that's very close to 1. The one after that, N sub E, is the number of those planets that are Earth-like in some sense. So small rocky planets with atmospheres on which life might emerge. Now, you may know there's a satellite, NASA satellite in orbit at the moment called Kepler, and it's looking for these extrasolar planets, and it's finding them by the hundreds. And it's finding them by the transit method when, if a planet passes across the face of its parent star, there's a slight dipping in the light from the star as a result of it being blotted out by the planet. And so this thing just stares at 300,000 stars day after day after day and looks for those little blips in the light curves. And as a result of that, many, many planets have been found, and it doesn't quite have the capability of finding other planets just like Earth, but it's getting close. And so you see newspaper headlines, much like this one. This was just last month. New estimate, billions of Earth-like planets in our galaxy. And that's, I wouldn't disagree with that. I think it's probably true that there are billions of Earth-like planets out there in the Milky Way alone. It's a lot of real estate on which life might emerge. So now we get to the next term in the Drake equation, F sub L. That's the fraction of Earth-like planets on which life actually emerges. What is that? Well, Frank Drake likes to put that equal to 1. There are a lot of scientists, certainly a lot of SETI astronomers, who say, given an Earth-like planet, life will obligingly pop up. In other words, it confuses habitability with inhabited. An Earth-like planet might be habitable, but that doesn't mean it's inhabited. And unfortunately, a lot of media reports just gloss over. They treat those two terms as if they're the same. It's just grammatically incorrect. And so, how likely is it then that given an Earth-like planet, life will pop up? Well, then that has to do with the problem of life's origin. How did life begin? We need to know how it began. And if we know how it began, then we can estimate the odds that it would happen on a planet like the Earth. If you don't know how it began, you can't estimate the odds. So how did it begin? Well, what did Darwin have to say on that? It's my favourite Darwin quote. It's mere rubbish, he said, thinking at present of the origin of life. One might as well think of the origin of matter. So Darwin, of course, famously gave us a wonderful theory that explains how life on Earth has evolved over billions of years, from simple microbes to the richness of the biosphere we observe today. But he pointedly left out of account how life got started in the first place. Mere rubbish, he said. So Darwinism only works once you've got life. Going from non-life to life is a big step, and it's the first step. And without that step, Darwinian evolution simply can't happen. So we have to get life in the first place. Now, it's interesting that we physicists have now explained the origin of matter, so knock that one off. Where are we with the origin of life 150 years after Darwin expressed these sentiments? Well, we're just as much stuck today as Darwin was in his day. We haven't a clue how life began. Plenty of theories, a few scrappy experiments, but basically we are in the dark about what it took for life to get going. Now, when SETI began, and when I was a student, searching for ET was considered so bizarre, one might as well have said that one was searching for fairies. And the reason is that biologists, almost to a person, said that life on Earth is a bizarre, complex freak accident, and therefore unique in the universe. That life, even the simplest form of life, is so stupendously complex, it would never happen again anywhere else. That it must have required a sequence of very peculiar circumstances to bring life into existence from non-life. So it was a chemical accident of such low probability that nowhere else in the observable universe would it happen. One sometimes sees the quite fallacious argument voiced that, oh, the universe is so vast, there must be life out there somewhere. Simply isn't true. Within the volume of space that we can, at maximum, in principle, have access, there may be 10 to the 23 potential sites for life. It's easy to imagine that the odds against life forming are much, much lower than 1 in 10 to the 23. Very easy to imagine that. Just imagine, for example, that to form life from non-life requires a succession of 10 chemical reactions. Surely it will be many more, but supposing it was just 10. Supposing each of these required a temperature range of, say, 10 degrees. So one might have to be between 10 and 20 degrees, and one between 40 and 50 degrees, and so on. And you needed to have them in the right sequence. Well, a bit of arithmetic will soon show you that the chances of getting that right sequence are going to be exceedingly, exceedingly low. And so it doesn't take very much for life to be seen as a bizarre freak. And that's the way it was treated for most of my scientific career. But in recent years, the pendulum has swung the other way. And we now have scientists like Christian de Duve saying life is almost bound to arise wherever there are conditions like the Earth. In fact, he even calls life a cosmic imperative, a wonderful idea that somehow life is built into the nature of the universe in a fundamental way. It's a life-friendly universe, and so life is going to pop up obligingly wherever we find it, wherever we find Earth-like planets. I'd love to believe that. The thing is that this sentiment that the universe is teeming with life, and contrasting with what it was like in the 60s, that life is confined to Earth, that switch in sentiment is not based on any science. It's not like we now understand how life began. We are just as much in the dark as we were. So it's entirely fashion that is leading people, including very distinguished scientists, to declare that there must be life all around the universe. We cannot know. The error bars are infinite. We simply don't know how life came to exist, and therefore we can't estimate the odds. So the big take-home message, I get infuriated. People say, well, do I believe there's life out there? The whole point is that we can't know until we do something about the error bars on the origin of life. And I'm going to tell you about what we can do. How can we test this hypothesis of the cosmic imperative? Wonderful if it's true. How can we test it? The answer is we need a second sample of life, what Chris McKay at NASA Ames calls life 2.0. We need to find a second sample of life that started from scratch, independently of life as we know it. So we want life, but not as we know it. We want to find a different type of life with a second genesis. Because if it's happened twice in the universe, then surely it's going to happen all around the universe. So we just need one other example. So how do we find that? Where do we look? How do we find life 2.0? Well, one is, of course, SETI. If we should pick up radio signal, well, they can tell us how life began. The other is that something called the Terrestrial Planet Finder. This is would be, if it was funded, a space-based system that could take that inventory of planets that Kepler is compiling at the moment and observe them in such a fine level of detail that the atmospheres of those planets could be imaged, and the spectrum of the atmospheres could be measured. And then perhaps this would reveal oxygen or something like that, which might be a telltale sign of life. But that's going to be a long time coming, many, many decades. It has to be a huge, very expensive space-based system. A lot of people think, let's go to Mars. We may find life on Mars, and then if there's life there, doesn't that mean it's happened twice, once on Earth and once on Mars? Unfortunately, it doesn't mean that, as the following picture explains. Mars and Earth take a hit from time to time from comets and asteroids with enough force to splatter rocks all around the solar system. And this means Mars rocks come to Earth, Earth rocks go to Mars. So if you get life on one of those planets, it's going to spread to the other one pretty quickly. For my money, I think life probably started on Mars and came to Earth later. So if we go to Mars and we find there's life there, chances are it's good old Earth life. So we're still no better off. All it says is that life we know has started once and it's spread around a bit. We need a second sample of life. Some people pin their hopes on synthetic biology. So if we could make life in the lab, in a test tube, wouldn't that show it's easy to make? Not at all. We want to know how nature did it without a big science grant, without a test tube, without all the fancy equipment, without the lab technicians, and in particular, without an intelligent designer, who for the sake of argument we could call Craig Venter, without an intelligent designer who knew what he was trying to achieve and could move towards it step by step. We've got to figure out how nature does it. So even if we manage to make life fairly easily in the lab, it doesn't show that it's easy to make in the great wide world out there. So what do we do? Well, what is the most Earth-like planet in the universe that we know? That's the most promising place to go to find a second sample of life. What's the most Earth-like planet we know? It is, of course, Earth itself. If life pops up readily in Earth-like conditions, as many scientists assert, then surely it should have started many times over right here on Earth, right on our home planet. How do we know it didn't? Has anybody actually looked? Well, astonishingly, until a few years ago, the answer was no. Nobody had thought to look on Earth for life, but not as we know it. All the textbooks will tell you, and I'm sure a teacher told you when you were at school, that all life on Earth is the same life. We're all interrelated, and even the bizarre organisms in the deep ocean volcanic vents, same life as us. Well, that's not true. All life on Earth so far studied is the same life as us. The problem is that most Earth life is microbial, and we've only just scratched the surface of the microbial realm. We notice the elephants, the oak trees, and so on, but actually, the life that is teeming on the surface and beneath the surface of our planet is almost all microbes. You can't tell by looking what makes a microbe tick. You've got to dig into its innards to discern its biochemistry. So if you go looking for microbes of our form of life, then of course that's what you find. If you go looking for A, you find A. You don't find B, which is what we're interested in, a form of life that is microbes with a biochemistry so radically different that it could not possibly have had a common origin. People always want an example. I can give you a very simple example. very easy to understand, though maybe not a realistic one. All life that we know is based on left-handed amino acids and right-handed sugars. The laws of physics are indifferent between left and right. And so you can make right-handed amino acids and left-handed sugars. You can buy them commercially. If life were to start over again, maybe there's a 50-50 chance it would be mirror life, that is with right-handed amino acids and left-handed sugars. You wouldn't find those if you went out, if you have a normal sort of culture medium based on the left and right stuff, you wouldn't find this mirror life. So that's one possibility, you see. And there are others, many others as well. I don't have time to go into it because I want to get back to intelligent life, which is what I think most people are interested in. And so the issue then is that if life had started many times, there could be literally aliens under our noses. Aliens, not in the sense of coming from space, though it may have done, as I explained. I think maybe even our life came from space, perhaps from Mars. But alien in the sense of a different tree of life and a different origin. So not just another branch on the known tree of life, but a whole separate tree. Sometimes it's called the shadow biosphere. And it could be all around us. It could be that intermingled among the microbes under a microbe slide, which you get from, say, a cubic centimetre of soil. That intermingled among the microbes that we can identify might be some which are this radically alternative second genesis. Very hard to find. But I want to move on to get back to SETI. Because if we do find the shadow biosphere, let me just make a strong claim. If there is a shadow biosphere, if we have life on Earth of a radically different form, when we actually make an effort to look for it, I think we could find it within about 10 years. And that term then in the Drake equation, that really problematic F sub L, that would go away. If we found a second sample of life, the way would be open then. Still plenty of other problems. Given you've got life, what is the probability of intelligence evolving? We don't know how to work that out, but at least we know what the mechanism is. It's Darwinian evolution. We understand that mechanism. We don't understand the mechanism that turned non-life into life. So we'd be in with a chance. So we'd be greatly boosted. But meanwhile, what can we do to help out these poor cash-strapped SETI astronomers? Well, the answer is that we can, I think, give up on worrying about messages deliberately directed towards us and look instead for more general signatures of alien technology. And by intelligence, we really mean we're looking for technology. That is there anything out there in the universe that looks fishy or could not possibly have a natural origin? It could be anywhere, and because, well, I think Arthur C. Clarke famously wrote that a sufficiently advanced civilization will be indistinguishable from magic, because we have no idea what alien technology that is 1 million or 10 million years in advance of ours, how it might manifest itself, it pays to be as broad-minded as possible. So what I'm about to tell you is exceedingly speculative, for the simple reason that we have to remove all our prejudices about what would alien technology be like. So traditional SETI is rooted in radio messages, radio telescopes. It's very, very anthropocentric, very parochial. I want you to expand your minds and think much more broadly about, in general terms, how might alien technology leave a footprint in the universe? How would it manifest itself in a way that we might be able to detect as something fishy? Well, there's one way that does involve actually using radio telescopes. So I've been talking about ET beams a message directly at us with deliberate intent. But there's another way of beaming, which is perhaps better compared with a lighthouse. The lighthouse sweeps around the horizon for the benefit of anybody who's out there. But the lighthouse keeper standing up here isn't waiting to get a reply. It's simply there as an altruistic symbol. So is it possible that an alien civilization has built something like a radio beacon or even a light beacon that's sweeping the plane of the Milky Way, maybe once every few months or few years, and it would just go bleep. It would sweep around and go once every year or two, you'd hear a bleep. Is that possible? Something like this. The Milky Way is very flat, like a disk, and so you don't have to go in every direction, just sweep the plane. Is that possible? Well, this would show up in a radio telescope if it's a radio beacon. as just a bleep or maybe a series of bleeps repeating after a long period of time. Now, I told you about the SETI astronomers. What they do is they look at a particular star for half an hour and then move on. They don't have the resources to stare at a fixed patch of sky for months or years on end. But that's what you'd need to do to discover these transient events, pulses. Now, it would make sense to stare at the center of the galaxy because that's where the oldest stars are, so potentially where the oldest and therefore richest civilizations are likely to be that may have made a radio telescope. Well, there was one moment of excitement in 1977 when, after the event, it was discovered that the Big Ear radio telescope in Ohio have picked up a bleep. Rather a long bleep, it lasted, I think, 72 seconds. And the astronomer who looked at this, that was back in the days when computers literally printed out this stuff on bits of paper. And the astronomer concerned wrote, "Wow," in the margin, because it was exactly the sort of thing they were looking for. In those days, they just listened to one particular frequency, Frank Drake's original choice, and it was a narrow band signal for very strong 72 seconds. And nobody, of course, knows what it was. It's never been heard again, in spite of the fact that the radio telescopes occasionally are pointed at that part of the sky. Was that a beacon? Was that something that will repeat, maybe in 10 years? Well, we don't know, because we haven't got the resources to keep monitoring that part of the sky. But let's go beyond radio astronomy. Is there anything else that we could look for out there in the universe? Well, if we can imagine that a very advanced technology or very advanced civilization would expand beyond the confines of its own planet and engage in large-scale astro-engineering. We've done terrestrial engineering, which, as I told you, could be seen from many light years away, things like the Great Wall of China. Maybe in another 10,000 years or million years, we will be doing astro-engineering or planetary engineering. So this is an old idea. One example is due to Freeman Dyson, the physicist at Princeton. It's called a Dyson sphere. So he said, imagine that a civilization expands and becomes so hungry for energy that it dismembers its planetary system and smears it out around the star and traps all of the light coming from the star. So this is like a solar energy project with a vengeance. You don't have mirrors out in the Arizona desert. What you have is you're capturing everything, all of the light. And Dyson spheres would show up as infrared objects, and some astronomers have actually, in a half-hearted way, gone to look for them. So they would be distinctive. They would have this distinctive thermal footprint if they're out there. So it just shows that there are things that we can look for. It's not a message. It's simply a signature of alien technology. Of course, if we saw something like this, we'd sit up and take notice, or something like this, perhaps. But, you know, it's a big universe, and it's very hard to know where to look. And I've pondered all this and discussed it very often with my wife. We were talking about Dyson spheres one day, and she said, well, why would the aliens be so stupid as to wait and, you know, pull their own planetary system to bits? Why not go to somewhere where planets are forming and plunder all that good stuff before it gets scooped up into planets? So I thought, well, that was a pretty neat idea. And here's a picture of one such. This is Beta Pictoris. So it's a proto-planetary disk. So this is a place where planets are forming. If you come back in a few million years, this will be a star with planets going around it, but it's still in the process of getting together. So if there is any alien civilization millions of years ahead of us, they'll be out there with their sky trucks and other heavy equipment, harvesting that material, maybe turning this into a Dyson sphere, maybe taking it away for some other purpose we don't know. So that's a great place to look for something fishy. Of course, we have to understand the system well enough to know what is fishy, but that's the sort of thing I have in mind, that this would be a place to look. But now, of course, all of this is a long way away. It's all out there in the galaxy. Wouldn't it be nice if we could search closer to home? And that brings me to something that often goes by the name of the Fermi paradox. The reason it's called the Fermi paradox after Enrico Fermi, who the Italian physicist genius, who just after the Second World War, incidentally, I'll show you, you know Fermi must be famous because here he is on an American postage stamp. For the physicists in the audience, so you probably know this, but the deliberate mistake up here This is supposedly the fine structure constant, but he's got it wrong. And so they conveniently cropped the picture so as not to give the game away. But anyway, that's Fermi. And what's Fermi got to do with this? Well, in, I think, 1948, he was sitting around at Los Alamos, where they made the first atomic bomb. He worked on that project. Sitting around talking to some colleagues about the UFO reports, which were very popular at the time. And he said, well, where is everybody? And what he meant by this is that the galaxy, we now know, is about 13 billion years old. The solar system's only about 4.5 billion years old, so there were stars and planets around long before Earth even existed. If the universe is teeming with life, as SETI optimists hope, then there will have been planets with life and maybe intelligent life long before Earth came into existence. And so we've been around 4.5 billion years. That's plenty of time for life to spread across the galaxy. So if there's just one civilization out there that thinks that it wants to spread beyond the confines of its home planet and maybe colonize others, it could have easily colonized the whole galaxy in the age of the solar system. And so Fermi reasoned that as they weren't here, if the Earth wasn't colonized a long time ago by aliens, therefore the aliens don't exist. And it's often called the Fermi paradox. Not paradox at all. It's one possible explanation. Of course, there are many ways in which the reasoning might be flawed, that is, in which the universe could have lots and lots of intelligent life, but they still haven't come here. In fact, there's a book, 50 resolutions of the Fermi paradox, so you can take your pick. But what I want to do is explore the scenario that maybe ET did come to the solar system, but they're not here. They're not still here. That is, Earth, or the solar system at least, has been visited sometime in the past by not necessarily flesh and blood aliens, but maybe by their robots or their machines or something of that sort, the products of their technology. And so then the question is, could we find traces of that visit? And it could have been an exploration, it could have been a colonization wave, it could have been an attempt at colonizing Earth and then moving on. Could be all sorts of reasons, might be reasons we can't even imagine. But let's suppose that the solar system had been visited by this advanced alien community. When would that have been? Well, I've explained to you that these communities, if they're out there, will have been around a long period of time. 4.5 billion years, the Earth has been here. Any time in that 4.5 billion year window, Earth could have been visited. So what's the expected time that they might come? You know, if you say, well, do the mathematics and work out the expected time, it's about half that time. Well, that's a bit pessimistic, and I think if there are civilizations out there and they're accumulating in number, you might expect visits rather more likely in the recent past. So let's take 100 million years as a good ballpark figure. So if ET had been here 100 million years ago, would we know about it? Is there anything left that we could find that would be a trace of alien technology that would survive for 100 million years? And the answer is not very much, but when I wrote the book, I thought up 3 things, and I'm open to suggestions about others. Just take you through them briefly before bringing this to a conclusion. There are 3 things I thought of that will be, as it were, alien footprints. The first is nuclear waste. So if these aliens had used nuclear rockets and they dumped some of that fuel, we could find that now. Nuclear waste famously lasts an immense period of time, and we could actually go and find it, in principle. We could find it. For example, if we found a lump of plutonium, this would be a dead giveaway because there's only one place plutonium comes from these days, and that's nuclear reactors. When the Earth formed, it would have had natural plutonium, but it's long since decayed. So if we find any plutonium anywhere, it's got to have it's either human or alien origin. And just to give you some idea of the power of this method of looking for ancient nuclear waste, this is a uranium mine in Gabon in West Africa. And this is famous because this uranium went critical 2 billion years ago. It was a natural nuclear reactor. It's not running anymore. The uranium's depleted. But the point is that by studying this, the scientists have been able to reconstruct the nuclear history of this particular configuration way back 2 billion years ago. So you see, we have the power to be able to reconstruct. If alien technology had been in the solar system, we find this nuclear waste, we have the power to reconstruct the story behind it. Now, there are another couple of things on this slide. Quarries or mines on Earth or near neighbours in space. If they're big enough, they would survive for a long period of time. Let me give you an example. You probably know that the dinosaurs were done in when a comet smashed into the Earth 65 million years ago and made a crater 180 kilometers across in what is now the Yucatan Peninsula of South America, Central America. That crater was only discovered recently because it's not in your face. You don't see it as you fly over. You need geological survey instruments. But you can find it, even though it's buried deep beneath rock strata. So any large enough mining or quarrying work, even if it's 100 million years old and buried, could still show up in geological surveys if you take trouble to look. Now, obviously, it would make sense if you saw something like this on an asteroid, and as you probably know, this is now a hot topic. We're going to go to the asteroids and mine them and all become rich. So if you got out there and you saw something like this, somebody had been there already, then that's a bit of a giveaway. The great thing about asteroids and the moon is they're airless, and so there's no erosion. Only what happens when smaller meteorites hit, and eventually those features go away. So the moon is another great place to look for signs of alien technology. And by happy coincidence, the Lunar Reconnaissance Orbiter, which is currently mapping the moon to half-meter resolution, let's go round and round, mission control is at my university, Arizona State University. Just across the way from my building is mission control for the Lunar Reconnaissance Orbiter. And they have these wonderful pictures taken of the moon. It's better than Google Earth. High-resolution pictures of the moon. They're out there on the internet. You can go look and see if you can see signs of artifacts on the moon. Now, I can tell you that the LRO people have found many artifacts on the moon. Many. But they're all human. They've said they can see the Apollo landing craft, they can see tracks left by astronauts and so on, they can see the Russian craft. So we know it has the power to detect artifacts on the moon. But, of course, there are tens of thousands of pictures. They haven't looked, they deliberately looked, they knew where to look for the human artifacts. There's been no systematic search done for any alien artifacts or alien engineering works or any sort of strange, anything fishy, let's put it that way. So this center at Arizona State University employs half a dozen students whose job it is, they pay them to just look through these pictures to see if there's anything worth remarking on. Of course, they're not really looking for ET, though I'm sure they'd tell us if they did, if they found it. They're looking for things like lava flows and rock formations. So the point is that this has the power. Now, the point I'm generally trying to make here, take-home message number 2, is this is all crazy, isn't it? Well, yes. Am I suggesting the aliens visited the moon? No, I'm not suggesting it at all. What I'm saying is that if there are alien civilizations, there's a tiny, tiny chance they would manifest themselves by having sent technology to the moon sometime in the very distant past. And because the moon is almost inert, we have the means of detecting the signature of that technology, and it doesn't cost any money. And that's the point. It's the money is the point. It costs us nothing. If we mobilize, say, school students, get them to look at these pictures and report what they see, it's not actually hitting the taxpayer dollar. So my feeling about doing SETI, or in fact doing any science, is it doesn't matter how speculative it is, how crazy it seems, so long as it doesn't cost anything, why not look anyway? And so that's the spirit in which I'm approaching this expanded SETI effort. We just do what we can do. Now let me turn to the third thing. I won't bother to go back to the slide. The third thing, which is the possibility of a message in a bottle. Could it be that ET has left us a message for posterity? That's a nice idea. Humans do this. If you're on an island, you put the message in the bottle, fling it into the sea. You don't expect to get a reply. You don't sit around waiting for a reply. So again, like the beacon, it's a one-way thing. Might an ancient civilization have left us a message in a bottle? Well, maybe. So we have to think, well, what would the bottle be, and how would the message be configured? And so there's the message in the bottle. And I think there's a very obvious answer. Very happily, nature has provided us with bottles and a means of messages. And the bottles are called living cells, and the medium for the message is called DNA. And so could it be that instead of sweeping the skies with radio telescopes in the hope of getting a message from the stars, we should be sweeping the genomes of terrestrial organisms in the hope of a message in the DNA of terrestrial organisms uploaded a long time ago by ET, maybe in person, more likely remotely. Viruses, for example, upload their DNA into cells all the time, retroviruses. So we know the means of doing it. You put the message in a virus, get the virus to upload it into the cell. Now, the point about this is that some of these messages in our genomes are billions of years old. We have genes that are hardly changed in tens of millions or hundreds of millions or even billions of years. So it's a great way of preserving a message. So this is nanotechnology. These are nano machines which will replicate and multiply, reproduce the message, the content, for immense periods of time. Now, there's an issue about mutations. We can come back to that in question time. So is this all pie in the sky? Is this totally fanciful? Could intelligent beings upload messages into the genomes of organisms? Is that credible? Absolutely it is. Craig Venter just did it. He uploaded his email address into the genome of an organism called Mycoplasma laboratorium. So it's very famous. So his email address and a quote from Feynman and some poetry or something, I don't know, his phone number, maybe. So we can do it. So if Craig Venter can upload messages into microbial genomes, surely ET can do it with millions of years of technology. So how do we go about finding this message? Well, same deal as looking at the moon. It doesn't cost anything or very much. We're sequencing those genomes anyway. It's all put out free on the internet. You can look through it for messages. Now, I wouldn't recommend looking through it line by line because, typical genome of a higher organism has billions of bits of information. But if you look through, the famous four-letter alphabet, if you look through and you saw something like that, you'd certainly take notice because that's, as in Jodie Foster in the movie, that's a sequence of prime numbers. So if we found that in a genome, we would surely think that that's a sign of alien tinkering. And so that's all it needs. It just needs a systematic approach to look through these genomes. So again, let me just, health warning. Am I suggesting that ET has left a message in the genomes of terrestrial organisms? No. I'm saying that there's a tiny, tiny probability that if ET wanted to communicate with us or leave us a message, that'd be a good way to do it. And that because we're sequencing, we're building up the database anyway, this genomic data, it costs us nothing to look through it. Who knows what else we might find? We might not find ET, we might make some other discovery. So that's the spirit in which I think we should search through. Now, I want to close. There are other examples as well. You can read them in the book. But I want to close by asking the question, as people often do, that what would ET be like? Because we're trying to second guess a civilization or an intelligence or a sentient being that might be millions and millions of years in advance of us. And the problem is always that people tend to think, well, what will we do? And what will we be like in 1 million years or 10 million years? And so most of the speculation about alien intelligence is of this sort. In other words, that these are scarcely disguised human beings and with minds, very much like human minds. Now, sometimes people agree that artificial intelligence and robotics will get to the point that we'll have some sort of instantiated post-biological intelligence of this nature, but it's still unmistakably humanoid, both in its architecture and in its outlook, its mentality. And I would have to get away from all this. My own feeling is that biological intelligence will be a very transitory phase in the evolution of intelligence in the universe. You can see at the moment, a lot of the intellectual heavy lifting is being done on our own planet, not by human beings anymore, but by things like Google and supercomputers. That in another 100 years, pretty much all the smart decisions and pretty much every area of human activity will be made not by human beings themselves, but by some designed and distributed system. I don't like the word computer and I don't like the word robot because we're talking about a future technology here that has no words to describe it, except that it's designed, and probably it's been designed by the designer of the designer of the designer of the designer, and so on, many generations into it. And that come back to Earth, if we survive for another 1,000 years, come back in 1,000 years, and almost all of the important intellectual effort will be done by these design systems. They may be biological. I mean, it may be components, biological components grown and fused with electronic components. It could be other types of technology we can't even guess at. But the ultimate would surely be to harness quantum physics. You probably have heard of the hope of building a quantum computer, which would represent a leap over a conventional computer as big as the conventional computer over the abacus. So the search for the quantum, well, search, but the quest to build a quantum computer is a multi-billion-dollar industry worldwide. And so if we can do this, if we can actually build a quantum computer, then the question is, can we build an intelligent quantum computer? So a really advanced intelligence might well be quantum mechanical in that nature. It's what Frank Wilczek, the physicist at MIT, calls quintelligence. And so this is an artist's representation of quintelligence. It's the whole of, well, if it were a conventional computer, it could be the whole of a surface of a planet, or maybe the whole of a Dyson sphere, turned over to some gigantic circuitry, great throbbing global megabrain, if you like. But if it's a quantum computer, quintelligence, it may be no bigger than a car. And that's because quantum computers work at the atomic level. And one quantum computer harnessing 300 atoms would already outcompute the entire universe as a conventional computer. So it only takes 300 atoms, and you've got a universe full of computational power. And so that doesn't leave much of a technological signature. Quantum computers are best built where it's very cold, and the coldest places are in the intergalactic spaces. So if there's something the size of a car in intergalactic space, sitting there merrily doing its quantum computing intelligence introspection, whatever quantum computers like to do, then chances are we're not going to know about it, and chances are that they're not going to be communicating. So that's a rather depressing note to end on. I hope that if there's a hierarchy of intelligence in the universe, and it's out there, and it may not be. I have to say that my default assumption is that there is no intelligence out there. But if there is, I would like to think that there is some thread connecting us with them, some commonality of purpose that would mean that even if they don't go out of their way to send us messages, they wouldn't go out of their way to conceal their existence. I want to finally finish by just mentioning, and this may come up, that the only authority I have to speak about SETI, apart from being a well-wisher and a bystander for these last 50 years, is I chair something called the SETI Post-Detection Task Group. If ET calls on my watch, it's my job to make the next step, like who do we tell and should we reply, things like that. And so this task group, I was lumbered with this job because Ray Norris, an Australian radio astronomer, was doing it first, and he got bored and handed it over to me. So it consists of scientists and journalists, and we have a priest and a couple of lawyers and some science fiction writers, and we meet from time to time to sort of wrestle with the problem, supposing we picked up some strange signal tomorrow, or supposing we had incontrovertible sign of alien technology, what next? Are we prepared for it? And it pays to be prepared. So that's my own active involvement in SETI. Otherwise, I'm just, as I say, a commentator. Well, you may have come to the conclusion then from this talk that it's all rather hopeless, that SETI is a glorious but almost certainly doomed quest. And why would anybody bother to do it? Why do we do SETI? We're looking for a needle in a haystack when we can't even be sure that the needle is in there. And I think the answer is shown by the people here today. You've come here today because, like me, you're deeply fascinated with the question, are we alone in the universe? You like to ponder on what it would mean if we share this universe with myriad other life forms. Because in a way, looking for ET is like a glimpse into our own future. If there are many civilizations that have made it through their little mini crises and have gone on to a glorious future, well, then we see in the sky a trajectory of the future of humanity. And so I think searching for them out there is, in a way, just searching for ourselves. And I think it's good, particularly for young people, to ask questions like, what is life? What is intelligence? Why are we here? Are we alone? These are all great things to ponder. These are the big questions of existence. We may not find the answers, but it's great that people ask those questions. And I can express it no better than in the words of Frank Drake himself: SETI is a search for ourselves, who we are, and where we fit into the universe. And I think at that point I will stop and take questions. Thank you.
Very interesting and very clear. You might have already touched on this, but if the universe is so vast, infinite, surely there must be more forms of life that only surely it's just not occurred on Earth. I mean, the probability must be huge that...
Right. You're throwing concepts and numbers around with gay abandon here. So, of course, if the universe is infinite, if it's infinite and homogeneous, then it's simple mathematics to show that not only is there going to be intelligent life out there, there'll be an identical copy of you. In fact, there'll be an infinite number of identical copies of you. So that's just a matter of probability. But I was very careful to say the observable universe. We can see out as far as what is called a Hubble distance. It's 10 billion light years, or 13 billion light years, something like that. We can't see beyond that because of the finite speed of light. And so within that volume, there are, I mentioned, 10 to the 23 potential sites. That's a finite number. And so the probability of life emerging has to beat that finite number. And it may do. If we knew how life began, we could attempt to answer that. But as we don't, it's entirely possible that it doesn't beat that number. And that's what was believed 50 years ago. And it may be right. We just don't know. That's why we need to find a second sample of life.
Hello. I'm interested in your views of the opportunity that could be offered by this upcoming square kilometre array to look for ET, given the death of the radio telescope array in America that you mentioned earlier that died because of lack of funding.
Yes.
Does the square kilometre array have an opportunity there?
It's been much discussed that the square, people who might not know what the square kilometre array is, it's a proposal to build over many dishes together a collecting area equivalent to a square kilometre. And there's a tussle going on between Australia and South Africa as to who's to host this. But anyway, if we get it, then of course we would have a very powerful instrument with a big collecting area. And certainly some attention has been given to using this for SETI purposes. Of course, it would have to piggyback on the more mainstream type of radio astronomy. But it's true because it is designed to pick up what started out as light just before the first galaxies formed, that are now stretched by the expansion of the universe into the sort of middle radio bands. That's exactly where you would expect to find radio messages if they are being broadcast to us. So it's in the right ballpark, and the question is, it's going to boil down to money and sensitivity. And I think I come back to the point that it would, even the square kilometre array would not have the power to pick up, say, a TV studio, even on the nearest star, planet going around the nearest star. It does not have that sensitivity. It's only if ET is beaming the message directly at us. And this is the point I want to make. They have to make a conscious effort that they know we're here and they're beaming at us. But I think that's not credible for another 1,000 years or so.
Yep. Just a question back to the probability of life.
Right.
We know on Earth that life arose quite soon after the formation of the Earth,
yes, right.
rather than 1 or 2 billion years after. So doesn't that show us that life is quite
likely? No, it doesn't, no. And I actually have a slide debunking that, but I didn't have time to show it. So Carl Sagan was fond of making this argument that life must be easy to make, he said, no sooner than was Earth ready for it, that up it popped. Now, the argument against it is a little bit subtle, but I think it's an important one. One way of putting it is that, well, it had better have started quickly, or we would not be here now. In another 800 million years, the sun will get too hot, it will boil the oceans dry, and there can be no life on Earth. So it's only a finite window of opportunity for life to emerge, evolve, and be observed. And so if life hadn't started until, say, 3 billion years after Earth began, it wouldn't have made it to intelligence, assuming that the time it takes to get intelligence on Earth is typical. We don't know that, and Charlie would be the first to argue that we can't really read anything into that. And so the rapid formation of life on Earth is consistent with life being easy to make, and it's also consistent with it being very hard to make. Can't let you tell anything. It's a sample of one only. We need more.
Well, following up a little bit on that, what would be your opinion on the suggestion that has been made that life on Earth might have formed a few times independently and then wiped off and then form again?
Right.
Is there any chance we could ever, find a bit more on that?
Yes, yes. And if you buy my book, you will read all about this, because people say, well, give me a scenario where there could be many origins of life on Earth. And I usually cite that one, that between about 4 and 3.8 billion years ago, the Earth was being bombarded quite mercilessly by very large asteroids. It's called the period of late heavy bombardment. And the biggest of those impacts would have boiled the oceans and possibly sterilized the whole planet. So there's a scenario that maybe life gets going in a quiescent period between two such impacts. And then, wham, it gets wiped out. And then it starts up again, wham, it's wiped out. And maybe that happens dozens of times. And then finally, we are the descendants of the one that just didn't get wiped out. But that was published back in the 80s. Since then, the feeling is that even the biggest of these impacts would not totally sterilize the Earth for the simple reason that it would propel a lot of material into solar orbit. And some of that material would carry the microbes with it. And cocooned inside the material, they would be safe in space conditions. And eventually, some of that would come back. So now we have the interesting scenario that life starts up, life one starts up, wham, swept off the Earth, around the sun, things go quiet, life two starts up, life one comes back. So now we have life one and life two coexisting on Earth, and then wham, happens again, life three, and so on. And so by the time all this settles down, you may have 50 different forms of life from 50 different origins commingled. And then the question is, would any survive to this day? And that's another story. Okay?
I was wondering if life one and life two are going to be detected, wouldn't we always say they have a common ancestor, because both the origin and evolution of life is dependent on the environment, and all of the Earth, if we consider that as one environment, regardless of where life started, we'd say it has a common ancestor.
Right, sounds like a line weaver argument.
Shouldn't be a surprise, I'm a student.
We have to, of course, define life. So the big problem about the origin of life is we don't even know whether this is a well-defined transition. I've been talking rather glibly about the transition from non-life to life. Was this like a phase transition in physics, going from water to steam, something like that, or a flame bursting forth at some particular critical temperature? So was there a critical threshold of complexity? Below that, not living; above it, boom, there's life. Or was it like a seamless transition from simple things through more complex things, more complex, more complex? So it's a little bit like, what is a mountain? You go walking in the hills, start out in the valley, you end up on the mountaintop. Where did the mountain begin? It's not very well defined. So we don't know that, but I'm assuming when talking about multiple origins that it's like the phase transition. And you can then say, no life down here, life above it, and that this is a separate transition from no life to life. And so they have a common ancestor in non-living things, but not in living things. So that you have to take that point of view, I think, to answer that question. Right.
Is there a factor in the Drake equation that talks about the potential longevity of a society that's as technologically advanced?
The last one, capital L, is how long would civilizations with radio technology last? And there's another very good example of the anthropocentrism that plagues this subject, because back in the 1960s, when SETI began, everyone was preoccupied with the Cold War, nuclear annihilation, and so on. And so Carl Sagan used to argue gloomily, well, probably any civilization that develops radio technology will develop nuclear weapons, and then they'll blow themselves up, so we could expect them to be around only for a few decades, you see. Well, then the Cold War went away, and people now are preoccupied with environmental degradation. So now when people are talking about SETI, they say, well, ET, so they won't blow themselves up, but surely they will manage their environment in a green and responsible manner. They would not be building radio transmitters that don't optimize the power output. So we should look for optimal beacons. And so, you know, we're applying our prejudices now from the 21st century. So in another 20 years or another 100 years, we may be preoccupied with something else, and we think, oh, ET surely will be worried about that thing, whatever that is. So I think the upshot is we simply mustn't have any preconceptions about what an alien technology should be like, and that therefore it pays to look in the broadest possible terms, or in anything fishy, as I keep putting it.
I was discussing, left-right shadow biospheres with colleagues 5 or 10 years ago.
Right.
Each side was eating on its own sort of food, except they had one common requirement, water or a cave or something. Then you'd get a drift if you had a random fluctuation to one of the sides being larger than the next. Then you get an inexorable drift towards eradicating the other side.
Right.
Just because reproduction is geometric and fluctuations.
Right. So this is the famous problem at the origin of homochirality, and I have a postdoc from NASA. She did her PhD thesis in exactly that subject, and so this is something that I'm very familiar with. You just need a tiny seed asymmetry and an amplification process. But the point is that seed asymmetry might be random. There's nothing to say that if it happens again on Earth, it's got to fluctuate the same way. It could fluctuate the other way. Now, we don't know that because we don't know what imprinted that asymmetry. It could be that it was imprinted in space already, and that amino acids were delivered to Earth with a preponderance of one over the other already built in, and maybe that's what tipped the balance. But we don't know that. And I gave the example of mirror life not because I think that is the most likely way that life might be different, but it's a very easy example to imagine, and it's very easy to see why a common origin will be ruled out. So it's a very clear-cut example, even if not a very likely one.